A suburban driveway in July. The blacktop burns underfoot. A man walks barefoot to the mailbox and winces with every step. He opens the electric bill, $340. 6 feet beneath those burning feet, the ground sits at the same temperature it held in January, 55 degrees. By the end of this video, you will discover why the industry that sells you cooling made certain you would never look down. Last spring, I drove 3.5 hours south to meet a man outside Bloomington, Indiana, who had been cooling his house with the dirt in his yard for over 4 years. I had seen his setup described in an off-grid forum. Blurry photos, a hand-drawn diagram, claims that sounded too clean to believe from a screen. So I went myself. What I found was not complicated. A standard central air conditioner sat on a concrete pad beside the house, running, doing its job, but wrapped around the smaller copper line coming off the compressor was something you would never see in a showroom. 100 feet of 3/8-inch soft copper tubing coiled tight around the high-pressure discharge line. Both ends ran underground through polyethylene irrigation tubing, buried about 18 inches deep in a loop across his side yard. A small aquarium pump circulated water through the buried loop and back through the copper coil continuously. I pulled out my infrared thermometer and measured the discharge line temperature with the loop disconnected, 161 degrees. Then he reconnected the pump and we waited 5 minutes. I measured again, 98 degrees. A 63-degree drop before the refrigerant even reached the condenser. I pushed a probe thermometer into the soil at 2 feet, 61 degrees. At 4 feet, 57 degrees. At 6 feet, the probe read 55 degrees exactly. On a day when the air above the ground was 96 degrees, the Earth 6 feet down had not moved a single degree from where it sat in January. I asked where he learned it. Not from a contractor, not from a manual, from his uncle, who had worked on commercial walk-in coolers for 30 years. That uncle learned it from a refrigeration mechanic in Arkansas. That mechanic learned it from the physics. This knowledge moves quietly through people who actually work with pipe and soil and compressors. It does not move through people who sell HVAC equipment. I stood there watching a system that does exactly what a $20,000 geothermal installation does. Same physics, same thermodynamic principle. His total material cost was $87. But what I measured in that yard is not new. The science behind it is older than the air conditioner itself, and the institution that just put a price tag on it is one of the most respected engineering schools on the planet. The United States Geological Survey operates out of Reston, Virginia, and has been mapping the thermal profile of American soil for decades. Their data confirms a fact most homeowners have never been told. Below the frost line, typically 6 to 10 feet deep, ground temperature stabilizes near the mean annual surface air temperature for that location. Across the temperate band of the country, that number falls between 50 and 60 degrees. For the majority of American suburban land, it centers around 55. Summer or winter, that temperature holds constant. The Earth is a massive thermal battery beneath every driveway and every backyard in the country. The physics that explains why goes back to 1852. At the University of Glasgow, a physicist named William Thomson published a paper that would reshape how the world understands heat. Thomson, later known as Lord Kelvin, described the theoretical foundation of the heat pump cycle. Moving heat from one place to another requires far less energy than generating heat from scratch. That ratio is called the coefficient of performance. It is the single most important number in refrigeration engineering. Kelvin's theory sat on paper for 60 years. In 1912, in Zurich, Switzerland, a mechanical engineer named Heinrich Zolli filed Swiss patent number 59350. Zolli was famous for steam turbines, but this patent describes something entirely different: a ground source heat pump, pipes buried in earth, fluid circulating through them, the constant underground temperature used as a heat sink in summer and a heat source in winter. The concept was brilliant. The timing was wrong. Cheap coal and oil made efficiency irrelevant, and the patent gathered dust. Then in the late 1940s in Indianapolis, Indiana, a tinkerer named Robert Weber had an accident that changed everything. He was experimenting with his deep freezer in the cellar. He touched the hot outlet pipe coming off the compressor and nearly burned his hand. That pipe was dumping heat the freezer had pulled from inside the box. Weber had a thought. What if he captured that waste heat instead of throwing it away? He ran copper tubing from the freezer's hot side down into the ground outside his house. Fluid circulated through the buried loop. It absorbed the Earth's constant warmth and released it inside. He connected a fan to push heated air through his home. The next year, Robert Weber sold his coal furnace. He heated his entire house with the ground. In Indianapolis, in winter. By 1948, the concept had gone commercial. Engineers installed the first successful commercial ground source heat pump in the Commonwealth Building in Portland, Oregon. That installation has since been designated a National Historic Mechanical Engineering Landmark by the American Society of Mechanical Engineers. In that same year, Professor Carl Nielsen of Ohio State University built the first residential ground source heat pump in his own home. The science was proven. The engineering community knew exactly what the ground could do. And at the center of all of it sat one physical fact. Water and earth have a much higher thermal conductivity and heat capacity than air. These fundamental physical properties mean they conduct and store heat energy far more efficiently. When your condenser tries to reject heat into 95 degrees Fahrenheit outdoor air, the compressor fights for every degree. When it rejects that same heat into 55 degrees Fahrenheit ground-cooled water, the compressor barely works. Same machine, same refrigerant, radically different electricity consumption. Peer-reviewed research confirms that swapping an air-cooled condenser for a ground-cooled condenser improves the coefficient of performance by 47 to 128%. Energy consumption drops 10 to 39%, not in theory, in controlled laboratory measurement repeated across decades. Every geothermal contractor in America charges $15,000 to $25,000 to connect your house to that 55 degrees. Robert Weber got there for free in 1948. The physics has been proven for over 70 years. So why did this knowledge vanish from American construction? That disappearance was not an accident. In 1902, a 25-year-old engineer named Willis Carrier stood in a Pittsburgh printing plant solving a humidity problem for a lithography company. The machine he built became the foundation of mechanical air conditioning. By the 1920s, the Carrier Corporation launched the Weathermaker campaign, positioning machine-cooled air as the symbol of American progress. Their trade publications framed passive cooling and earth contact approaches as primitive, unsanitary, backwards. A 1930 Carrier technical manual dismissed earth contact cooling as suitable only for cellars and food storage. The machine had arrived. Everything before it had to be erased. The erasure was systematic. In 1927, the first model mechanical codes emerged in the United States. HVAC industry representatives sat on the drafting committees. By 1945, the post-war building boom had standardized air-cooled mechanical systems as the only acceptable approach to cooling American homes. Passive alternatives vanished from architectural education. ASHRAE codified air-cooled mechanical cooling as the baseline assumption for every thermal comfort calculation in the country. The technology was not disproven, it was removed from professional memory. Think about what that means for the contractor who shows up at your house. He was never taught this in trade school. It was never on his licensing exam. His supply house does not stock the parts because the code does not recognize the system. The building inspector cannot approve what her training never covered. An entire chain of professionals locked out of knowledge that a retired homesteader figured out from a forum. The money behind this exclusion is staggering. The United States HVAC market was valued at over $31 billion in 2025. 88% of American households use air conditioning. Residential air conditioning alone consumed 254 billion kilowatt hours of electricity in 2020. That is 19% of all electricity used in American homes. Families opening July utility bills at kitchen tables and setting them face down because the number makes them sick. That sickness funds an industry. The Air Conditioning, Heating, and Refrigeration Institute spends hundreds of thousands of dollars on federal lobbying every year. Lobbyists walking the hallways of Capitol Hill with research they commission themselves. In 2019, an ASHRAE technical committee rejected a formal proposal to create a performance pathway for ground-coupled cooling in American code. The committee cited insufficient domestic data. It ignored 3 decades of European installations. The committee's membership showed majority representation from HVAC equipment manufacturers. The people deciding whether you can cool your home with the ground are the same people who sell you the machines that replace the ground. Open the International Residential Code to Section M1601. Ductwork must be constructed of specific fire-rated materials. There is no provision for earth contact or water contact air handling outside the building envelope. A system that circulates ground-cooled water around a discharge line does not fit the template. It cannot be approved. Not because it fails, because the form does not have a box for it. Every air conditioner sold is a compressor running at maximum head pressure against hot outdoor air. Maximum head pressure draws maximum electricity. Every dollar flows to the utility. Every burned-out compressor flows back to the manufacturer as a replacement sale. A buried loop tapping 55-degree Earth cannot support a $31 billion industry. Now, if you do not own land, if you are not off-grid, if you are sitting in a suburban house or an apartment right now, stay with me. Because what comes next works in any home, costs under $300, and requires 0 permits in most jurisdictions. This part was built specifically for you. Here is the number I promised you. The United States Geological Survey mapped the ground temperature beneath every region in America. In most of the continental United States, 6 feet down, the temperature is approximately 55 degrees. It does not change in summer. It does not change in winter. That number means the earth beneath your driveway is already at the exact temperature a $20,000 geothermal system is engineered to reach. The resource is not hidden. It is not rare. It is 6 feet beneath your property right now. A geothermal contractor charges thousands to access that temperature. What you are about to build reaches it with hardware store materials and a weekend of digging. The concept is simple. Instead of letting your condenser fight 95-degree air, you wrap a copper coil around the hot discharge line and circulate ground-cooled water through it. The earth pre-cools the refrigerant. The compressor runs under reduced head pressure. Your bill drops. Here is what you need: 100 feet of 3/8-inch soft copper refrigeration tubing, $25 to $45, 50 to 100 feet of 3/4-inch polyethylene irrigation tubing for the buried loop, $20 to $40, one small submersible pump rated at 200 gallons per hour, $12 to $18, brass compression fittings or barb adapters, $6 to $10, thermal paste or aluminum tape for the contact points, $4 to $6, zip ties, $2 to $3. Total material cost runs $70 to $120. Step 1. Identify the high-pressure discharge line on your air conditioning unit. It is the smaller diameter copper line running from the compressor to the condenser. It will be hot to the touch when the system runs. The larger line is the suction line. It is cold. You are working with the hot side only. Step 2. Coil the copper tubing tightly around the discharge line. Secure every 6 inches with zip ties. Apply thermal paste at every contact point. Maximum surface contact means maximum heat transfer. Step 3. Connect both ends of the copper coil to the polyethylene tubing using compression fittings or barb adapters. Make sure connections are tight. Step 4. Dig a trench 4 to 6 feet deep, well below the surface layer where temperatures fluctuate with the weather. Run the polyethylene tubing through it in a loop across your yard. Backfill and pack the soil. Step 5. Connect the pump to circulate water through the buried loop and back through the copper coil while the air conditioning runs. The earth cools the water cools the refrigerant, the compressor runs easy. This is functionally what a $20,000 geothermal ground loop does. A standing drum of water heats up over the course of a day. The buried loop never runs out of thermal mass. The earth absorbs and dissipates heat across an enormous volume of soil. This is the difference between a workaround and permanent performance. 3 safety points. You are not cutting or modifying the sealed refrigerant circuit. The coil wraps around the existing line. It does not penetrate it. Insulate exposed copper above ground to prevent condensation near electrical components. Make sure every fitting is secure and the pump is rated for continuous operation. Monitor your discharge line temperature with an infrared thermometer. If it drops below 90 degrees, reduce the water flow immediately. Overcooling the discharge gas can cause premature condensation, leading to liquid backup that disrupts system pressures and strains the compressor's mechanical valves. Keep the discharge line between 95 and 110 degrees. That is the sweet spot, where the compressor runs easy and the equipment stays safe for years. The earth under your driveway has been sitting at 55 degrees this entire time. The only thing between you and it is 18 inches of dirt and an industry that would rather sell you a new compressor every 12 years.